Welcome to lecture number 10 on measure and integration. Let us just recall that in the previous lecture, we had started looking at the notion of outer measure. So, let us recall how the outer measure was defined and what are the properties the outer measure has. Given a measure mu on a algebra A of subsets of a set X, the outer measure induced by this measure is a set function defined on the class of all subsets of the set X. So, it is a function defined on the power set of X, of course, taking non-negative values, and it is defined as for a set E in subset of X, look at a countable disjoint countable covering of the set E by elements of the algebra A. Now, and look at the size, the measure of the set A I. So, that is mu of A I, add up the measures of all the sets A I, so that this union covers. So, that gives you a number which we can think of as approximate measure of the set E. So, look at the infimum over all such possible coverings of E. So, mu star of E is the infimum of all summation mu of A I, such that union of A I's cover E. And we proved properties of this set function, the outer measure, namely mu star is monotone, it is countably subadditive, and on the sets in the algebra mu star is same as A. So, mu star extends the measure mu, but it is only monotone and countably subadditive. So, let us look at an example of this outer measure. So, we will in this example, we will start with the collection A of all subsets of the real line, which are either finite or their complements are finite. So, recall in the beginning of the lectures, we have shown that this collection A is an algebra of subsets of A. So, this collection A forms an algebra of subsets of the set R. Let us define a set function mu on this. Mu of the set A is equal to 0 if the set is finite, and if the set in the algebra is not finite, then we know its a complement is finite. So, in that case we define mu of A to be equal to 1 if A complement is finite. And we have also checked this example, for this example, that mu is a measure on this algebra A. So, I would strongly suggest that you try to prove it yourself once again, that this mu is a measure, that is mu on the algebra A is countably additive. So, let us denote by mu star the outer measure induced by mu on all subsets of the real line. So, mu star is the outer measure given by this particular measure, and we want to find some properties of this mu r of this outer measure mu. And if you recall, just now we said outer measure always is monotone and it is countably subadditive. So, these properties are true for any outer measure. So, in particular this outer measure also. We want to do something more, and obviously, let us note that mu star of x, the whole space, is same as mu of x, and that is equal to 1, because mu star extends. So, and x belongs to the algebra, actually x complement is empty set which is finite. So, by definition mu star of x should be equal to mu of x, which is equal to 1. And if A is any subset of x and mu star being monotone, so we know that mu star of A is less than or equal to mu star of x, and that is less than or that is equal to 1. So, mu star of every set is going to be between 0 and 1. So, this is a property we have deduced from the general facts that mu is monotone and mu star of the whole space is equal to 1. We want to show that if A is a countable set in real line, then mu star of A is equal to 0. So, let us see how do we show that. So, let us take a set A. So, let A contained in R A countable. That means, I can write A as a sequence. So, x 1, x 2 and so on. So, I can write A is actually equal to union of singletons x I I equal to 1 to n. And by definition, mu of the singleton x I, it is a finite set. So, that is equal to 0 for every I. Thus, mu star of A, which is less than or equal to summation mu of x i's. This is one covering, and measure of each one of them being equal to 0. So, this is equal to 0. So, mu star of A is less than or equal to 0. We know it is always bigger than or equal to 0. So, that implies that mu star of A equal to 0 if A is countable. So, we have shown that for a countable subset in the real line, the outer measure which we defined is going to be 0 whenever A is countable. Let us go further and look at some other properties of this outer measure. We want to show that mu star of A is equal to 1 if and only if A is uncountable. So, let us prove that. So, let A contained in R, A uncountable, claim mu star of A is equal to 1, right. So, note mu star of A is less than or equal to 1, that is obvious, right. That is by the definition we said mu star is monotone, which is equal to mu of x anyway, mu star of x. So, mu star of A is always less than or equal to 1. To show that mu star of A is also bigger than or equal to 1. Okay. Now, let us note A uncountable. Okay. So, look at A is uncountable. So, what can you say about A complement of the set? Okay. It cannot if A is uncountable, then we want to if A is uncountable, let us take a covering of A I equal to 1 to infinity. Let us take a covering where A i's belong to the algebra A, right. Now, note in this covering A uncountable implies at least one of these A i's, at least one A I is uncountable. So, this is the observation which is going to be crucial. A is a subset of unions A i's which are in the algebra, okay. And each one of them, if A is uncountable, then each one of them cannot be countable, because if each one of them is countable, then countable union of countable sets will be countable. So, A will be countable. So, that means there is at least one A I which is uncountable. Say A I naught is uncountable, but that will mean what? A I naught is uncountable means, so thus we have got that mu of mu star is A I naught is uncountable. So, mu of A I naught, okay. What can we say about that? So, that cannot be equal to 0. Can we say that cannot be equal to 0? Let us see. One of the A I is not is uncountable, right. So, that means this is not finite, okay. Right. So, this is because A I naught belongs to the algebra A, that is a crucial thing. So, that means either A I naught is finite or its complement is finite, but we know that A I naught is uncountable. So, that means A I naught uncountable. So, that implies that A I naught complement is finite, because it belongs to the algebra. So, either A I naught has to be finite or its complement has to be finite. So, this is finite. So, that implies that mu of A I naught by definition is equal to 1. So, that is what we have shown. So, thus A is contained in, if A is contained in union A I 1 to infinity, then for some I naught, mu of A I naught is equal to 1. So, that implies, that automatically implies the fact that mu star of A, okay, the mu star of, so any covering will have at least one of the elements, so implies this is bigger than or equal to 1, right, because mu star of A is the infimum of, because mu star of A, the summation I equal to 1 to infinity mu of A I is going to be bigger than or equal to 1, right, because A I naught is 1, at least one of the terms is 1. So, for every covering A I of A, sigma mu of A I is bigger than or equal to 1. So, the infimum has to be bigger than or equal to 1. So, hence mu star of A is equal to 1. So, we have proved. So, therefore, thus A uncountable implies mu star of A is equal to 1. And the converse is obvious, because conversely, right, conversely if, so conversely if mu star of A is equal to 1, then A is uncountable, because for countable sets we have already shown mu star of A is equal to 0. So, A is uncountable if and only if. So, we have shown, we have characterized all sets for which outer measure is going to be equal to 1. So, we have shown the fact that mu star, the outer measure induced by the measure that we are looking at, namely mu, if mu of A is equal to 0 whenever A is finite, and mu of A is equal to 1 when A complement is finite. And if we look at the outer measure induced by this measure, then that has the property that mu star of every countable set is equal to 0 and mu star of a set is equal to 1 if and only if the set is uncountable. So, that is the property that we have. So, mu star of A is equal to 1 if and only if A is uncountable. Now, let us we already know that mu star is going to be is countable, is subadditive. We want to know is mu star additive, right. So, we will show that is not the case, that mu star is not even finitely additive. So, to show that, let us observe that the real line I can decompose into two disjoint sets minus infinity to 0, 0 closed, union 0 to infinity. So, the real line is written as a union of two subsets, and now the outer measure of the set minus infinity to 0, that is an uncountable set. So, that is equal to 1, and the outer measure of 0 to infinity is also equal to 1. So, outer measure of both of these sets is equal to 1, their union is R, and so we get mu star, and mu star of R is equal to 1. So, which is strictly less than 2, equal to sum of the outer measures of each one of them. So, that says mu star of R is strictly less than mu star of minus infinity to 0 plus mu star of 0 to infinity. So, this should be mu star and this also should be mu star. So, that says that the sets that mu star, the set function mu star is not even finitely additive. But let us observe some more facts about this outer measure. This outer measure on all subsets is not finitely additive, but it has some nice property. It is countably additive on a subclass. So, let us look at the subclass to be S, which is A subsets of R, all those subsets of R where either A or A complement is countable. So, keep in mind A or A complement is countable. We had shown that this collection forms a sigma algebra, and our given algebra A, which was the collection of all sets for which A or A complement is finite, obviously is a subset of this class S of subsets which are A or A complement countable, and that is of course, a subset of all subsets. So, algebra A is contained in S, this sigma algebra S, and which is inside of P R. And it is actually we have also shown that mu star. So, what is mu star on S? If a set A is countable, then mu star of A is 0, right. If it is not countable, but then it is A complement is countable, right. Then if A complement is countable, then the set A cannot be countable, it has to be uncountable, and for uncountable sets mu star of A is equal to 1. So, mu star restricted to S is the set function which is mu star of a set A is 0 if A is countable, and mu star of a set A complement of A is equal to 1 if its complement is countable. So, and that we have already shown is a measure on the class of on all all sets in the sigma algebra S. So, given that measure in our example, given the measure on the algebra A, when we define the outer measure which is defined on all subsets of P R is not even finitely additive, but if we restrict it to the collection of sets S which is A or A complement countable, then on that class it is a measure and it extends. So, the given measure on the algebra does not extend to all subsets, but at least it extends to a collection, a sub collection of all subsets, and that includes the original algebra. This is a situation which we are going to see is very common in our extension process. So, we are starting with a measure mu on an algebra, and just now we said in the process of extension, let us define outer measure on all subsets, and here is an example which says to all on all subsets outer measure is not, it may not be even finitely additive, but at least this example says that we can probably find a subclass of all subsets of that set X, which includes the given algebra, and on that probably it is countably additive. So, the problem is to look for a collection of subsets on which it is going to be countably additive. Before we go over to that process, let me give you an exercise which all of you should try, namely, if mu is a measure on an algebra, then we define the outer measure as infimum, look at all coverings and look at summation mu of A I, right. There was no condition on the put on the sets A I, and the exercise says if you take only those coverings of E by elements of the algebra which are pairwise disjoint, and then take the infimum over only such coverings, that also will give you the outer measure. So, the exercise is that outer measure for a set E can be defined in terms of countable disjoint coverings of E, namely take coverings of E by elements of the algebra, and the elements of the covering are pairwise disjoint. Look at the sum mu of A I and take the infimum over such covering. So, infimum is taken over all countable disjoint coverings. In the original definition, we did not put this condition, and the exercise is both of these are same, and the answer lies in the simple observation that when a measure mu is defined on an algebra and you look at the union of elements in the algebra, any union can also be written as a union of pairwise disjoint sets. So, a union of elements of the algebra can be represented in terms of pairwise disjoint sets. That fact we have used earlier also. So, using that you can try to prove this exercise. Here is another exercise which you should try to prove to get familiarized with the concept of outer measure. Let us take X any non-empty set. A is an algebra of subsets of a set X, and let us fix any element x 0 in X, any arbitrary element. Now, given any subset A in the algebra, either x naught will belong to A or x naught will not belong to A, two possibilities. So, if x naught does not belong to A, that particular element that you have fixed does not belong to A, put mu of A, define mu of A to be equal to 0 and define mu of A equal to 1 if x 0 belongs to A. So, whenever x 0 is in A, the measure of that set is 1, otherwise it is equal to 0. Show that this is a countable additive set function, namely it is a measure, because mu of empty set is automatically 0. So, we would like you to characterize that, show that the outer measure, look at the outer measure induced by this measure, show that the outer measure has the property that outer measure of every set is either 0 or 1 again, and outer measure of a set is equal to 1 if the element x naught belongs to A. That is a property of mu also. So, we want you to show that mu star of A is equal to 1 if x 0 belongs to A. Can you say that the converse is true? Namely, we would like you to also show that mu star of A is equal to 1 implies x 0 belongs to A, but that will be you will need the condition that if x 0 belongs to A, because x 0, the singleton x 0 may not be in the algebra. So, that makes a difference. So, check look at this exercise and try to prove the facts asked for. That will help you to understand what is an outer measure, how does the outer measure of a set change with given conditions. Let us look at now the problem. You are given a measure mu on an algebra A of subsets of a set X. You have defined the outer measure, which in general is countably subadditive. So, how to pick up sets, how to pick up those subsets of X such that mu star restricted to them will become countably additive, as happened in the previous example that we discussed. So, for that is what is called the concept of a measurable set, a subset E of X. So, mu is fixed, mu on the algebra is fixed, mu star is defined via that measure mu. So, mu is fixed. So, we are saying that a set E is mu star measurable, mu star is the outer measure induced by that measure, is called measurable if for every y in X, mu star of y can be written as mu star of y intersection E plus mu star of y intersection E complement. So, be careful, this says we are saying E is measurable. So, E measurable means take the set E, right, which you want to test whether it is measurable or not. So, divide any set y into two parts, y intersection E and y intersection E complement. Then measure of the two pieces should add up to give you the measure, the size of mu star of y. Okay. So, this is a picture here that you have got, this is my set E. Okay. I want to check whether it is measurable or not. So, take this E. So, take any set y. So, this is my y. So, that gives me this piece, which is y intersection E, okay. And this is the part, that is y intersection E complement. So, the requirement is, we are saying that E is measurable if using E, y is the set, cut it into two parts, y intersection E and y intersection E complement. So, there are two disjoint pieces of y, and we want you should have mu star of y is equal to mu star of y intersection E plus mu star of the other part. Okay. That should happen for every y, it should happen for every y, that is important. So, that is called this, we say that E is measurable if for any subset y, divide y into two parts, y intersection E and y intersection E complement. We want measure of outer measure of y should be the sum of these two outer measures. So, that is when we say a set E is measurable. So, let us look at so let us will denote by S star the collection of all mu star measurable subsets. So, whenever a set E satisfies this condition, we say that is measurable, and let us put all the measurable sets in a collection and call that as S upper star. So, S upper star is the collection of all mu star measurable subsets of X. Here is one observation, that a set is measurable if and only if mu star of y, we want definition says it should be equal to the sum of the pieces, but it is enough to say that mu star of y is bigger than or equal to mu star of y intersection E plus mu star of y intersection E complement. That is because for every set y, y is equal to y intersection E plus union y intersection E complement, and mu star is always subadditive. So, that means mu star of y is always less than or equal to mu star of y intersection E plus mu star. So, the inequality less than or equal to is always true, because mu is monotone. So, to verify whether a set is measurable or not, one has to check only that mu star of y should be bigger than or equal to mu star of y intersection E plus mu star of y intersection E complement for every set y. So, only bigger than or equal to has to be checked, and so we have to check only bigger than or equal to, and in case mu star of a set is infinity, then this inequality is obvious. So, that means one has to check this inequality only for sets for which mu star of y is finite. So, that gives us a very a simplification, saying that a set E is measurable if and only if for every subset y of x, with the property that mu star of y is finite. One has to verify that mu star of y is bigger than or equal to mu star of y intersection E plus mu star of y intersection E complement for every subset y with mu star of y finite. So, this is the condition we are going to use again and again to prove whether a set or check whether a set E is mu star measurable or not.